Welcome to the European Space Agency, ESA. This is the Robotic Learning Center, and today we're going to answer some questions about robots and how they're used in space.
What do robots have to do with space? Space and other planets have hazardous and challenging environments. Extreme temperatures can change the properties of stable substances. Look at what heat does to popcorn. Or what happens if you lick an ice lolly right out of the freezer. In space, temperature and other conditions are even more extreme. Take the International Space Station, the ISS. The side of the ISS facing the Sun reaches temperatures of 121 degrees Celsius, while the dark side plummets to minus 157 degrees Celsius. Meteors can collide with it, and because there is no protective atmosphere in space, the ISS is constantly exposed to the effects of potentially dangerous radiation. So, if anything on the outside of the ISS needs to be repaired, it is quite hazardous for astronauts to fix it. It's also one of the reasons that we can't directly explore the surface of Mars. So, what's the solution? Unlike humans, robots don't need food or oxygen to operate and can be designed to withstand the kind of extreme conditions found in outer space. This makes robots the ideal tools to work with as we prepare the way for the future exploration of our solar system. So what is a robot? Most experts agree that a robot is a device that has elements of electronics and mechanics. It can be capable of decision-making and may even be able to work autonomously. We can agree that this certainly is not a robot. However, the European Robotic Arm, or ERA, is clearly a complex robot. Robotics involves a collaboration of different disciplines: mechanics for motion, electronics for sensing, and computer science for thinking. We call this synergy mechatronics, and this means that to create a robot, people from different disciplines need to work together as a team.
In this DVD, we will look at the three disciplines of mechanics, electronics, and computer science that make it possible to design and build such complex machines. I've asked friends from Austria, Switzerland, the UK, and Sweden to lend a hand, and we'll be going on board the International Space Station to get help from ESA astronaut Thomas Reiter and Russian cosmonaut Mikhail Turin.
This is our first step to understanding robots. You might ask what Thomas is doing and what those arm movements have to do with robotics. Well, most robots are machines that move. They use a complex system of gears, levers, and brakes to move their various joints and take them in different directions, much like we humans use our muscles, bones, and joints. Robots use mechanics to move or manipulate objects. Where there is gravity, robots can use friction to move. They can use wheels, tracks, or legs. The type of footwear they use really depends on the surface. Let's have a robot race to find out which one of these magnificent machines is the fastest. We have two finalists, but what about the different surfaces? As you can see, the design and efficiency of a robot involves many different factors, depending on the kind of work they will be doing and where they will be doing it. In orbit, we are in free fall and so feel weightless. Therefore, wheels and legs are not much use. How does the Canadarm2 move payloads around the International Space Station? Just watch what Thomas is doing. He's using the handrails, which line the ISS walls, to pull himself along. Robots are often modeled on human design, and here, at the end of the Canadarm2, we find its hand, known as the end effector, which allows it to walk along the ISS by connecting with different grapple fixtures. Basically, it's holding on to the sides of the ISS. This robot uses thrusters to get around. To get an idea of how thrusters work, blow up a balloon and set it off. To add some control to the experiment, you can add a straw and a string. Since the balloon is now guided by the string, all of the propulsion power is directed in a straight line rather than in random directions. Many space robots use electric motors. Of course, this model of Era has no motor. That's why Thomas needs to move it himself. Robots require electrical energy to power their motors. We can obtain energy chemically, as in, for example, this lemon battery. The acid in the lemon acts as an electrolyte, ferrying electrons from one metal to the other. We can also generate electricity by harnessing the power of water or by burning fossil fuels. These students are demonstrating how to collect and store solar energy. The black bottle gathers much more energy in the form of heat than the silver bottle. However, modern solar panels generate electricity directly, like this solar-powered car. Or this solar-powered car. The wings of the ISS are actually solar panels that generate electricity that is stored in rechargeable batteries. These solar panels are made up of large numbers of photovoltaic cells. The sun emits particles of light energy called photons. These photons knock loose electrons from the material of the cell, which produces an electric current. The solar panels on the ISS will eventually deliver about 110 kilowatts of electrical power, enough to supply 20 average homes with light and heat. But how do electric motors actually work? Well, this is all down to electromagnetism. If you send an electric current through a wire, it creates a magnetic field around the wire. This allows the wire to be moved by an ordinary permanent magnet. To increase the effect, we coil the wire. The greater the number of coils and the stronger the current, the more powerful the magnetic field. What do robot mechanics have to do with the cuckoo clock? Look inside. Gears are an important part of machine movement. They allow us to control speed and power more precisely. Take the bicycle, for example. A big wheel at the front and a small wheel at the back. Hold on, I said a small wheel at the back. Better. Each time we turn the big wheel, the smaller wheel turns a much greater number of times. Gears allow machines to transfer energy at differing speeds to suit their design. The shuttle arm has gears and brakes in its joints to ensure accurate and controllable movement. The Era's elbow, wrist, and shoulder joints work as a system of gears and other mechanisms. Do you know what we mean by degrees of freedom? No, it's not a measurement of how strict your teacher is. The number of degrees of freedom in a robotic arm is the number of independent movements that it can make. Some joints, like your elbow, have just 1 degree of freedom, up and down. Your wrist adds more. These movements are also known as pitch, yaw, and roll. Your shoulder also has 3 degrees of freedom. The more degrees of freedom, the more movements we can achieve. The Canadarm2 and Era have 7 degrees of freedom because they each have 7 independent joints that can move separately. Robots can be programmed to do similar actions to us. However, the human hand is a truly amazing design. Not only do our hands have several degrees of freedom, we are among the few species which have opposing thumbs and fingers. Thumbs may seem pretty ordinary, but without them things would be a lot harder. The piano playing doesn't sound quite the same. Thumbs give us added dexterity. However, in some situations, even our unique ability isn't enough. On a spacewalk, astronauts must wear a spacesuit to protect themselves from extreme temperatures and exposure to radiation. This can really make things awkward. Thomas's artistic ability won't make much difference to space exploration, but what if Thomas needs to use a computer? Back on Earth, we can see the same effect. It might be best to stay away from instruments while wearing oven gloves. In robotics, the challenge is to build a robot with the same dexterity as the human hand. This simple model is pretty much how the Canadarm2 end effector works, and it suits its purpose very well. Robots can enhance human skills like precision, power, endurance, and speed. In weightlessness, astronauts could move the space shuttle, but it would be exhausting. However, Canadarm2 can easily and precisely move objects with a mass of 100 tons. It's not just mass, but momentum that needs to be controlled. Robotic arms are designed with this in mind.
The ability to move is just one feature of a robot. If they are to work in space autonomously, they need to be able to sense their surroundings.
From 2007, Europe's automated transfer vehicle will be one of the International Space Station's supply spaceships. Every 12 months or so, an ATV will haul 7.5 tons of cargo to the station 400 kilometers above the Earth. An onboard navigation system will guide the ATV towards the ISS, where it will dock automatically with the station. How does it know where to dock? What is the difference between this intelligent docking system and this much simpler robot? The answer lies in environmental awareness. Robots use a variety of sensors and electronics to gather information about their environment. The information robots gain through sensors is essential for taking decisions, modifying actions, and accomplishing tasks. If you wanted to protect your lunch, this basic photocell could help. It reacts to light and sets off an alarm. Not so fast. But how do robot sensors operate in space? The robotic arms use sensors to locate objects and then use a manipulator to pick them up or move them around. A Zero uses contact sensors to sense objects around it and avoid becoming stuck. But can it get out of this tight corner? It sure can. Robots can be designed to take in visual, auditory, chemical, temperature, motion, and pressure information. All sensory data needs to be translated into electrical signals that the robot can understand. So, how does a robot get a sense of its environment? Well, ERA, the shuttle arm, and Canadarm2 all have cameras and motion sensors built into their joints. The cameras installed on ERA are no ordinary cameras. They use infrared or IR technology, similar to your remote control at home. But what is infrared? Well, it is part of the electromagnetic spectrum, which is the range of all electromagnetic waves, like visible light, X-rays, and microwaves. Electromagnetic waves travel at the speed of light, which is 300 million meters per second, or about 1 billion kilometers per hour. What differentiates the waves from each other is their wavelength, which can range from thousands of kilometers to smaller than the nucleus of an atom. One of the most important and useful things about these waves is that they can travel in a vacuum. Human sight is restricted to the visible light section of the spectrum, the band of colors that make up white light. Robots, however, can see far more of the electromagnetic spectrum. For example, if you drink something cold, an infrared camera can see the temperature change. When you imagine a wave, you usually picture something that looks like this. Sound waves, however, look very different to what you might expect. Sound moves in longitudinal waves which look like this. Unlike electromagnetic waves, sound waves need a medium to travel in. Sound can't travel in the vacuum of space, outside the ISS. These satellite robots are called spheres, and they determine their position by using ultrasound, sound that is above the upper limit of human hearing. The spheres sense signals from 5 beacons mounted on the ISS walls. A Zero can be controlled using a normal TV remote control, which it detects with its infrared sensors. Rockvis is mounted on the outside of the ISS. It is testing joint technology, ground control, and feedback, and uses stereo vision cameras. Humans also see in stereo vision. Ever notice that the perspective from one eye is slightly different to the other? Try getting really close to something and it is even more noticeable.
So, robots use many different ways to sense their environment, but the big question is how a robot uses the sensory information it has gathered to make decisions and take action.
This sphere satellite can sense that the other is moving. But how is it still able to dock with the other sphere's satellite? We've already seen that robots can sense and do things, but this information is useless unless the robot acts on it or takes a decision based on the information. Decisions require a control system. These students are applying similar principles to navigate their way through this gym. They can't move unless told which line to follow by their controller. So every time they come to a junction, they have to stop and ask for a decision. But where is the control system for robots? Well, many robots can be controlled in real time by humans. However, robots can also be autonomous or self-controlled. But how do we implement autonomous behavior and self-control in a robot? As we saw earlier, robots need to have sensors that monitor their environment. They also need a controlling mechanism, generally a computer system. And very importantly, they need a feedback channel to relay information between the sensors, the controlling mechanism, and the parts that move. Robots like the ATV can autonomously control and adjust their behavior during a task. However, the initial motivation to do a task does not come from the robot's free will. Unlike humans who often spontaneously decide to do things, a robot needs to be programmed. We also need to program rules for how a robot takes decisions. The main elements used in programming robots are algorithms. An algorithm is basically a set of instructions that tell the computer to perform a specific task. Algorithms are a bit like recipes. Just like a recipe, you need to follow each step of the algorithm precisely. Otherwise, you'll create a mess. Turn on the hot plate, break the eggs, add them to the pan, cook for 1 minute, and serve. You can't miss any step. Uh-oh, he missed step 1. Turn on the hot plate. Break the eggs, add to the pan, cook for 1 minute, and serve. Okay, step 1. He's turned on the hot plate, but he didn't break the eggs. He has missed step 2. Just like an algorithm, every step has to be followed in order, or it means disaster. But what if the recipe is written in a different language? In order to follow any recipe correctly, it needs to be in a language you can understand. So what language do computers use? There are many different kinds of computer language, such as C and Java, but they all rely on digital technology. A digital system is one that uses discrete values. For example, the exact length of this MP3 player is 7.1486311, but we can approximate it to 7.1 centimeters. A light switch with a dimmer is analog because it has a continuous range of brightness. A light switch which simply turns the light off and on is digital. Digital can't be misinterpreted. The signal is either on or off. There is no room for error. The principle that voltage is either there or not, that a switch is on or off, is the basic principle behind the most complex computer system. Computer language is based on a binary number system. The binary system contains only 2 digits, 1 and 0. This means that every number has to be represented as a sequence of 1s and 0s. In the binary system, 1 is still 1, but the number 2 is represented by 1 0. 3 is 1 1, and 4 is 100. All numbers can be expressed by these two binary digits, or bits for short. Bits are the basic letters of computer language. Binary sequences, combinations of bits, are the words. When words are combined together, they form sets of data and instructions that the computer follows as a program. To make things easier for us, computers are programmed using English-style languages, which are then translated into ones and zeros. Programmers are able to give instructions like run when they want a program to start. In order to make a decision, we have to be able to act on this stream of ones and zeros. One of the most basic elements for decision-making is a logic gate. There are 3 basic logic gates: AND, OR, NOT. The output of an AND gate is only 1 when both inputs are 1. The output of the OR gate is 1 when either of the 2 inputs are 1. And finally, the output of the NOT gate is always the opposite of the input. Even the most sophisticated computers can only make simple decisions and perform very simple manipulations of ones and zeros. The secret is that they make these calculations very, very quickly. ERA is an interesting case. It doesn't just sense its environment, it is programmed with the space station environment, just like having a built-in 3D map. So rather than just sense obstacles as it approaches them, ERA already knows where everything is. Collision avoidance algorithms running in the ERA's microprocessor means that it can't bump into the sides of the ISS. Think about how you might feel if you had to walk everywhere to give people messages instead of just telephoning. Even electromagnetic waves like light, radio waves, and microwaves take a certain amount of time to get from A to B. It's straightforward enough to measure the speed of an electromagnetic wave. All you need is some marshmallows, and a wave generator. We call this special instrument a microwave oven. The microwave generated by the oven will heat the marshmallows at the peak areas first. These are the points at which the wave is strongest. At these points, the marshmallows will melt fastest. The distance between the melted spots is half the wavelength of the microwave. The frequency of the microwaves generated by this oven is written here on the back. All we do now is work out the average wavelength and multiply by the frequency. The product is the speed of the wave, which is very close to our earlier figure for the speed of light. Pretty accurate. So, all waves need time to get from place to place. The Sphere's satellites use this to their advantage. On the International Space Station, there are 5 beacons to help Spheres navigate. They do this using infrared and ultrasound. One Spheres robot sends out an infrared pulse which, since light travels so fast, is seen effectively at the same time by all the beacons and robots. The robots then wait for the beacons to send out ultrasound signals. All 5 beacons take turns to send out an ultrasound pulse. Sound is much slower than light, so each of the Sphere's satellites can hear the signals at a slightly different time. This means they can work out their position on the ISS and relative to each other. This time delay is an advantage for the Sphere's satellites, but this is also what makes autonomy essential for deep space exploration. The best way to communicate with the ISS, satellites, and robots on Mars is to use radio waves. These are electromagnetic waves, and we've seen that they travel at the speed of light, nearly 300 million meters per second. Look again at our line-following students. They have to wait before they can take the next step. If they could make their own autonomous decisions, they would be much faster. Humans can directly control robots on Earth where turnaround times are negligible. However, a robot on Mars will need to have a certain level of autonomy because even when Mars is at its closest, a radio signal will take 4.4 minutes to reach Mars. This means that a human operator would have to wait 8.8 minutes to see if the robot moved when instructed before giving the next instruction. For this reason, the ExoMars rover will be automated.
In this DVD, we have learned that the development of robots involves a synergy between three disciplines:
mechanics for motion, electronics for sensing, and computer science for decision-making. This synergy is known as mechatronics. Robots are machines that move. The mechanism that a robot uses depends very much on what the robot is designed to do and the environment it will be working in. Most space robots source their energy from solar energy. In space, astronauts are exposed to radiation, extremes of temperature, and have to wear protective clothing which restricts their movements. Under these conditions, robots can assist astronauts with hazardous or very precise tasks. Robots can be designed to sense through sight, touch, and sound. Most sensors rely on the electromagnetic spectrum. Robots also use ultrasound, infrared, and chemical sensors to get information about motion and position. Robots can be controlled in real time by humans, but they can also be autonomous or self-controlled. This will be important because of the time delay between Earth and Mars. Robots are programmed using algorithms, sets of instructions similar to very complex recipes. We use digital technology as the basis for communication with robots.
Robots may lead us further into space, but where they go, we will follow.
Robotic systems are necessary in order to assemble large structures in space which human beings can't handle by themselves. Humans have the ability to handle small tools, but they can't handle structures which have a large mass or a large volume. These can only be handled by robots. It is, of course, a great experience if you are in space to have an assignment outside the ship, and here robotic systems can be of enormous help. When I was 11 years old, I was able to observe Neil Armstrong tread on the surface of the moon. Ever since then, I've wanted to do the same myself. I will most likely be too old to stand with my own 2 feet on another planet, but the next generation may actually stand on the surface of Mars.